Hey everybody. Today we're going to look at how we can write net ionic reactions. That is to say, a different way to represent our chemical reactions that really gets at what chemical constituents are changing. What we've been working on so far is writing our chemical reactions. This is what we typically use when we have a statement, like words representing a chemical reaction. We would rewrite that, we'd translate that into a chemical reaction, reactants to products. It also does a really nice job representing what's happening on the benchtop in the laboratory when you're mixing things. But we also want to get a deeper understanding of the chemical reactions and really emphasize what's changing in our chemical compounds. The total ionic is a kind of a step towards that. We don't often use the total ionic reaction except in these cases when we're trying to get the net ionic equation or in advanced situations where we actually care about the spectator ions in solution. The net ionic equation is really what we want to be looking at. This looks at just those chemical compounds in the reaction that are changing. Those things that are actually going through either a precipitation acid-base or redox reaction. And this is what we want to focus on in this video. So when we write our chemical reaction, there's a couple things we need in order to have something that goes from chemical reaction to net ionic equation. First off, thing number one, we have to make sure that all of the compounds in the reaction are good compounds. That is to say, we need things that really exist. We need to make sure we're accurately representing what we're mixing. They need to be charge balanced. So this is particularly for ionic compounds. The positive charge, negative charge balance needs to be correct. If we don't have those things, you're going to end up in a situation where your reaction is either impossible to actually do, impossible to balance, or you just get the wrong representation of what's actually happening. Once we have that, all the compounds are good, then we'll want to balance the chemical reaction. This is going to be useful this week and necessary next week. This week, a balanced chemical reaction is going to make it so that the spectator ions, those things that aren't changing, properly cancel out on both the reactant side and the product side. And next week, this will be totally necessary. Then we're going to start looking at the chemical compounds themselves. And if it's a metallic solid, a gas or a liquid, we're not going to break that compound up. This might make more sense when we look at an example in just a moment. But let's get these rules down first. So metallic solids, gases, and liquids, those aren't going to break apart in a water solution. And when I say break, I mean the bonds are not going to disassociate. The chemical bonds are not going to give off any energy or change. Covalent bonds also do not break. There's a special exception for those covalent bonds that are extremely polarized. That's acids and bases, but those are special. Most covalent bonds, they do not break just from the interaction of water with the bonds. And then ionic bonds, we're going to check the solubility rules on our periodic table. If the compound is on the soluble side, those ionic bonds will break, covalent bonds won't. If it's on the insoluble side, those ionic compounds will stay as solids. Let's look at some examples. So, you will notice that these two reactions are the ones that we did in the predicting products demo video, which hopefully you already watched. And we're going to follow the same steps we were just looking at. The first thing we're going to do is we're going to translate the statement into a chemical reaction. Silver nitrate is going to be AgNO3. With, that's going to be plus. Copper wire, that's just going to be copper. We predicted the products for this already, and that's going to go to CuNO3 plus Ag. We want to put on the states of matter. We've got to make sure, oh, actually, before states of matter, let's check our charge balance. Silver is typically a +1 ion using our common ions list. Nitrate's -1, so that's nice and charge balanced. Copper wire, that's just pure solid wire. Copper nitrate, this one's a little bit tricky. We know that copper could be +1 or +2, and we don't know which this one is. It's not specified. At this point, you'd get credit for either copper +1 or copper +2. Either way you did it. I just happen to know that it's more likely that this is copper 2 nitrate, so I'm going to go with copper 2 nitrate. And then silver. Again, this is going to be silver metal as the product, and that's going to be solid silver. To figure out what's happening with the silver nitrate and the copper nitrate, solubility rules, but as mentioned, nitrates are always soluble is a good thing to remember. So we'll put that as aqueous, and nitrates are always soluble. We'll put that as aqueous. Balancing coefficients would be 2 and 2. Right? I needed, since I have the 2 nitrates, the subscript 2 tells me how many nitrates are in this compound. In order to get those 2 nitrates, I need 2 of these silver nitrate compounds because there's only 1 nitrate in each of these. And then I have 2 silvers, so I better end up with 2 silvers. This is the chemical reaction. We can then go ahead and write the total ionic, where the aqueous compounds, we already checked the solubility rules, aqueous compounds are going to break into their ionic constituents. So the total ionic would be 2 Ag plus aqueous plus 2 NO3 minus aqueous plus copper. Metallic solids do not break apart, so that's going to be copper solid. Goes to ionic compounds that are aqueous break apart. That's going to go to copper 2 plus aqueous. And again, +1 would have been fine, but I know it's +2. Plus 2 NO3 minus aqueous plus 2 Ag solid. Ooh, scrunched on the corner there. Now, to get to the net ionic, we want to cancel out those things that are exactly the same in the reactants and the products. So if there's something that has, let me make a quick note of this. When I say exactly the same, I mean same compound, same charge, same state of matter. And really same number. In the balanced reactions. So if we have something that is the same compound, same charge, same state of matter, same number, that is to say something that doesn't change between our reactants and our products, it's chemically boring. We don't really care about it. So in this reaction, we're going to notice that the nitrate, first off, the silver and silver. Let's go in order. Here we've got silver aqueous, here we've got silver solid, here we've got silver plus, here we've got silver no charge. So silver has changed in this reaction. We want to keep that represented. Here we go from 2 nitrates with the -1 charge in aqueous to 2 nitrates with the -1 charge in aqueous. Exactly the same. The nitrate is actually not changing at all. It is a spectator ion. It's also considered the counter ion. It's just there for the charge balancing in the silver nitrate and the copper nitrate, but it's not actually participating in the chemical reaction. So we're going to eliminate that as we go to write our net ionic equation, which would be 2 Ag plus aqueous plus copper solid goes to copper 2 plus aqueous plus 2 Ag solid. The charges matter. And you'll notice here what this net ionic equation is trying to show us is it's trying to show us where the chemical change is actually occurring. This says I don't care what the balancing negative charge is, what the balancing anion is. If I've got silver ions in solution with copper solid, I'm going to have this reaction, which hopefully you also can recognize as a redox reaction from the changing charges. And this redox reaction, all we need is these things in solution together to make this redox reaction happen. The nitrate, that's just there to balance. So this is the net ionic, really focusing in on the chemical reaction. Go ahead and try this one for a moment, and we'll do it together in just a sec, but get started on that, at least write the chemical reaction associated with it. Notice, this time I am specifying the charge on the copper, and that's important. Okay, let's go ahead and do this one together. So we're going to start by writing the chemical reaction. We're doing copper chloride mixed with sodium carbonate, and it's copper 2 chloride, remembering that this copper 2 tells us the charge on the copper. So it's going to be CuCl2, 2 chlorines to balance the +2 charge there, plus sodium carbonate, NaCO3. This goes through a metathesis reaction, flipping the cations with each other, and we're going to get NaCl plus CuCO3. And I did not give myself enough space, but we'll fix that in a moment. First, we want to make sure that we've got our materials charge balanced properly. Cu has the +2 charge. We're told that in the name, copper 2 chloride. So we need 2 Cls, each with a -1 charge. To charge balance that, we've got +2, -2. In the sodium carbonate, CO3 carbonate is a -2 charge. So in order to charge balance this, I'm going to need 2 sodiums, 2 +1s, to balance the 1 -2. So I've got +2, -2, that is charge balanced. NaCl +1 -1 is already charge balanced. And then copper carbonate, CuCO3, +2, -2, already charge balanced. So we can go ahead and start looking for our states of matter and our balancing of chemical reaction. The balancing, I think, is pretty easy. We've got 1 copper on product side and 1 copper on reactant side. We've got 1 carbonate on product side and 1 carbonate on reactant side. If I have a 2 in front of the sodium chloride, this tells me I've got 2 NaCls. This subscript 2 tells me that I've got 2 sodiums bonded to the carbonate. So they're ionically bonded to the carbonate. So there's 2 sodiums in this compound. There's 2 sodiums if I've got 2 sodium chlorides. 2 chlorines in copper chloride. 2 chlorines if I have 2 sodium chlorides. So that's the balanced reaction. To get our states of matter, we're going to have to go over the solubility guidelines. Sodium carbonate, sodium compounds are always soluble. That's one of the ones that's good to remember, so we'll go ahead and toss aqueous there. This is where I didn't give myself enough space. We'll toss aqueous there. Good enough. Copper chloride is the one that we should check. So if you look at the solubility guidelines, you see in the soluble rule number 3, chlorine, bromine, and iodine are soluble. So we think this is soluble, except with silver, lead, copper +1, and mercury +1. So this is actually really important because copper +2 and copper +1 actually have different solubility rules. So knowing that this is copper +2 is really important for us to be able to say that that's aqueous. Insoluble rule number 2 says carbonates are insoluble. So we know that this copper carbonate is going to end up making a solid. From this, we can go ahead and write our total ionic equation. The aqueous ionic bonds break, so we're going to have copper 2 plus aqueous plus 2 Cl minus aqueous. Notice these Cl's, this is not Cl2 bonded to copper. This is 2 Cl minuses ionically bonded to copper. So there's not a covalent bond there. So I'm going to have 2 ionic bonds disassociated in the aqueous solution, so I get 2 Cl minuses from that. Same thing happens here with the sodium carbonate. I get plus 2 Na plus aqueous, and then plus CO3 2 minus aqueous. Notice the covalent bonds in this polyatomic ion do not break apart. I leave the covalent bonds between the coppers and oxygens together. I didn't give myself quite enough space, so we'll cheat a little bit and just put our arrow here. We'll have 2 Na plus 2 Cl minus, states of matter, of course, aqueous, and plus Cu, CO3 solid. Now we want to go ahead and cancel out anything that's spectator. That is to say, anything that is not changing between the products and the reactants. Copper plus 2 is getting taken up into the copper carbonate solid. That's changing states of matter. That's going to be something interesting. 2 Cl minus aqueous goes to 2 Cl minus aqueous. That's boring. Let's get rid of that. 2 Na plus aqueous goes to 2 Na plus aqueous. Boring. CO3 2 minus, that's going into the solid. That's interesting. So our net ionic equation for this reaction would be Cu2 plus aqueous plus CO3 2 minus aqueous goes to CO3 solid. So what's nice about this is we cut through most of the noise in terms of what's happening, what chemical compounds we're mixing together, and we're really just accentuating the fact that we've got 2 aqueous compounds making a solid. This is a precipitation reaction, and it's also telling us it doesn't matter how copper ions and carbonate ions get into solution together. If you have copper plus 2 ions in solution with carbonate minus 2 ions, they will form a precipitate, regardless of how they get in solution. If they're in solution with each other, you get a precipitation reaction occurring. So this was the first redox reaction in the demo, and this was the second precipitation reaction in the demo. Let's look at a couple others, and then I'll have some for you to try. So here's 3 reactions we'll do together, and then I'll give you a couple to work on your own. Hydrochloric acid mixed with sodium hydroxide. Sodium carbonate put into hydrochloric acid, and magnesium metal burnt in oxygen. Let's go ahead and start with the hydrochloric acid one. Hopefully this one's pretty straightforward. HCl plus NaOH goes to NaCl from that flip-flop plus H2O. H2O is a liquid. NaCl from our common solubility rules is aqueous. NaOH is also aqueous. And HCl, being one of our strong acids, is also going to be aqueous. Because there's a big difference in electronegativity between the H and the Cl, this acid is going to dissociate. This will give us the total ionic equation of H plus aqueous plus Cl minus aqueous plus Na plus aqueous plus OH minus aqueous goes to Na plus aqueous plus Cl minus aqueous plus H2O liquid. Oof. Okay. And we'll notice that almost everything in this is, well, there's the chlorine is spectator, the sodium is spectator. We've got same charge, same element, same state of matter, same number. Those cancel out. And for this acid-base reaction, we get H plus aqueous plus OH minus aqueous goes to H2O, liquid. Right? We don't break apart liquids. These are also covalent bonds. We wouldn't break those. So this is our representation of that reaction that really just emphasizes the fact that there's an acid reacting with a base to produce water. If you are used to doing the H3O plus representation, that's something we get into in more depth in later chemistry classes. For this quarter, H plus for our strong acids is fine. Let's go ahead and work on the next one. This is sodium carbonate put into hydrochloric acid. This is also going to be an acid-base reaction, but it's our special carbonate reaction. So I wanted to do an example of that. We'll start by writing down our things. NaCO3 plus HCl goes to, from our prediction, you'd form the carbonic acid, which breaks apart into H2O liquid plus CO2 gas plus NaCl. Let's make sure our compounds are good. Oh, yeah, we need to make sure we're charge balanced, so we need 2 sodium ions to balance the charge of that carbonate. We also know, since this is a sodium compound, that it's going to be soluble in water. The HCl is going to be, since it's a strong acid, is also going to be aqueous. The CO2 is a gas that's produced, and sodium chloride is soluble in water. One point of contention here is whether we should put sodium carbonate as a solid or if we should put it as an aqueous. And this is because in the reaction I did, I actually poured solid sodium carbonate into the solution. But the reaction didn't occur when it was solid. The reaction occurred when it was dissolving in the solution. So to represent how the reaction was actually occurring, we're going to put it as aqueous because this reaction was happening in that water environment. Going to our total ionic, to Na+, right? This is an ionic bond. It's aqueous, so it's going to break apart. The covalent bonds in the CO3 in the carbonate do not break apart, but it is an ion floating in solution. The acidic bond does break apart. And this is the problem with doing this when I'm not in a classroom with people. I forgot something, and we'll talk about that in just a moment. So when we look at this, you'll notice a couple things. You'll notice, first off, when I go to cancel my sodiums, they don't cancel. I've got 2 sodiums, I've got 1 sodium. They have the same charge, same element, same state of matter, but I forgot to balance my chemical equation, which means when I go to get my net ionic, I'm going to have some problems, particularly in the fact that there's not enough hydrogens here in order to actually make H2O. So if I was balancing my chemical equation, I would have 2 HCl and 2 NaCl. I need 2 HCl in order to react to form, if I'm forming the carbonic acid, that's H2CO3. I need those 2 hydrogens. Also, H2O, I need those 2 hydrogens. That means I'm going to have 2H plus here, 2Cl minus there, and I'm going to have 2 Na plus there and 2 Cl minus there. So if you have that situation where your spectator ion is not canceling out, there's a good chance that there's a problem with your balancing, or you're doing really advanced redox reactions in weird conditions, but that's for next quarter. Let's go ahead and cancel out our spectators, the things that aren't changing. Now our 2 sodiums and our 2 sodiums will cancel. Our 2 chlorines and our 2 chlorines will cancel. And this reaction essentially says if I have carbonate ions in solution with acidic conditions, that is to say there's some acid there, I'm going to form carbon dioxide gas and, sorry, I didn't give myself enough space, H2O liquid. Right? And this gives us that kind of acid-base condition we're looking for, where there's an acid reactant and water as a product. In this situation, the CO3, the carbonate ion, is acting like a base. And we'll talk more about that in future classes. But in this class, we only have hydroxide as our typical base. There are other compounds that can behave like bases. And we'll get more into that in the future. Let's do this last example together. Magnesium metal is burnt in oxygen. This idea of burning is actually pretty much a hint. Burning is a special type of redox reaction. So the fact that we've got this burning is indicative of the fact that this is going to be a redox reaction. We've got magnesium metal reacting with oxygen. Oxygen is a gas. This is going to form magnesium oxide. And that oxides are actually not on the solubility guidelines, but they are not soluble. Most situations are not soluble. You'll also notice that this is metal and oxygen gas. There's no water in this reaction either. We'll go ahead and balance it. 2. Going to our total ionic, we've got a solid, we've got a gas, we've got an insoluble solid, and no water present. So we end up getting the exact same thing. And that means our net ionic equation is actually just the same thing. Typically, when we have these situations where the chemical reaction and the net ionic equation are the same, you wouldn't have to go through all of the steps. If you just write net ionic is the same as chemical reaction, that's good enough. But I just wanted to show, if you've got these situations, it is possible to have the chemical reaction, the total ionic and the net ionic, to all be the same. Okay, to finish out the chemical reactions we did in the demo video, we just have 3 more. I'm going to go through these pretty quickly. So do me a favor, at this point, pause the video and try to do the net ionic equation for all of these. Did you pause the video? Did you finish? Okay, let's do it together. We've got silver nitrate. It's a nitrate, so we know it's going to be aqueous. We're going to mix that with sodium phosphate. It's a sodium compound, so we know that's going to be aqueous. We don't even need to check our solubility rules. If we remember those two, sodiums are always soluble, nitrates are always soluble. It'll save us time. Phosphate has a -3 charge, so we're going to need 3 sodiums to charge balance that. We're going to do our flip-flop reaction. We're going to go to silver phosphate, and we're going to go to sodium nitrate. Now, for the silver phosphate, I check the solubility rules. Phosphates are insoluble. That's insoluble rule number 5. So that's going to be solid. That's going to be aqueous. I'm going to balance the chemical reaction. 3 sodiums, 3 silvers, 3 there. 3 sodiums, 3 nitrates, 3 there. And then I'm going to go ahead. Once you get good at these, I'm going to skip the total ionic. Once you get good at these, you can start to see like, oh, nitrate, nitrate, sodium, sodium. Those things are almost always spectators because they don't precipitate. So this is going to end up being 3Ag plus solid plus PO4 3 minus aqueous. Sorry, solid. Aqueous. Ions in solution are always aqueous. You don't have ions that are solids. That doesn't make sense. So Ag plus aqueous, phosphate aqueous forms Ag3PO4 solid. Boom. Acetic acid with sodium hydroxide. We'll start by writing down our chemical reaction. This is going to be CH3COOH. It's an acid. We'll put it as aqueous mixed with sodium hydroxide. It's a base. We'll put it as aqueous. It's a sodium compound. We'll do our flip-flop. That's going to form H2O liquid because we've got our base and our acid. And we are going to form sodium acetate, NaCH3COO aqueous. On the solubility rules, number 2, acetate compounds are soluble. So sodium acetate, also it's a sodium compound, so super soluble. The sodium is going to be a spectator ion, and the acetate is actually going to be a spectator ion. So this acid reaction is going to be this H here, H plus aqueous, plus this OH here, OH minus aqueous, goes to H2O liquid. That is a pretty common thing we see for our net ionic equations for acids and bases. In future classes, we have to be careful because this isn't a strong acid. It does not 100% disassociate. So in future classes, this idea of the acetic acid just becoming H+, that's not going to be entirely true. Watch out for that whenever you start working with weak acids in the future. Sodium iodide mixed with aqueous chlorine. So we've got our sodium iodide. Sodium compound is going to be aqueous. Notice here they give us the state of matter. Chlorine is typically a gas. We have to be given the state of matter to get the fact that this is Cl2 aqueous. Otherwise, I would have assumed it was a gas, but it specifically says aqueous chlorine. We're going to do our flip-flop. We're going to get NaCl plus 2 ion 2. This is, of course, aqueous. It's sodium chloride. And the iodine, it would be hard to predict from this whether the I2 that's formed is a gas or if it is aqueous. And the way that we're able to tell is because we actually did the experiment and we saw that it stayed in solution. So we know that this is going to be aqueous. If we did this reaction and we saw this violent bubbling and gas being formed, we might have that as the gas state, but we saw that it just formed a brown liquid. Again, skipping the total ionic just to the net ionic, I can see chlorine is going to change. This is covalently bonded chlorine. This is not 2 Cl minuses. This is Cl2. This is aqueous chlorine. This is ionic. Actually, maybe I'll do total ionic for this one. It's a little bit trickier than I thought. Oh, and I put the 2 in the wrong spot. Better. Okay. So, oh, and I need another 2, don't I? Before I go to my total ionic, let's balance this thing properly. 2 sodiums, 2 sodiums, 2 iodines, 2 iodines, 2 chlorines, 2 chlorines. Now we're looking good. 2 Na plus, aqueous, plus 2 I minus, aqueous, plus Cl2 aqueous. Covalent bonds don't break. Goes to 2 Na plus, aqueous, plus 2 Cl minus, aqueous, plus I2 aqueous. Ionic bonds break apart. I've got 2 sodium chlorides. That's going to break apart into 2 sodiums and 2 chlorides. I2, covalent bond, does not break. Now the spectators in this case are actually just the sodium. The sodium is the spectator here. The chlorine is actually an important participant in the reaction. So we get 2 I minus aqueous plus Cl2 aqueous goes to 2Cl minus aqueous plus, weird, I2 aqueous. That is our net ionic equation for that last reaction. Sodium isn't doing anything interesting besides balancing the charges. And what matters here is we've got a difference in electronegativity. This is a redox reaction. Hopefully, these few practice problems will make it so when you do your types of reactions lab, you'll have a good sense of how to do your net ionic equations. I'll also point out that about half of the reactions we just did are actually in your types of reactions lab. So if you were paying attention, some of the work's already done for you. If you got questions, come to office hours.